Hey everyone, welcome to our two-part series on DeepQ learning. In this first video, we'll dive into the theory behind DeepQ learning and unpack how it works. In the next video, we're going to put this theory into practice, coding an AI agent to conquer any Atari games. At the end of the day, who doesn't have a childhood dream to beat the Atari games? So let's begin. In our previous discussions, we delved into Q learning, a reinforcement learning technique where a Q function updates a Q table, essentially the agent's memory. Each time it takes an action, the agent's subsequent actions are determined by the updated Q table. And once training converges, we achieve an optimal training policy via an optimal Q table. However, Q learning has its limitations, especially due to its tabular nature, which becomes cumbersome in large state and action spaces. It's simply not scalable, as efficiently representing these spaces with arrays and tables becomes infeasible. For instance, let's recall the taxi agent from our last video, which dealt with just 500 states. Contrastingly, an Atari game presents a far more complex environment. Here, we use still frames from the game as input. A single frame in Atari is composed of an image of 210 by 160 pixels. Given that the images are in color, there are 3 channels. Each frame is 210 by 160 by 3 array with pixel values ranging from 0 to 255. This results in an astronomical number of potential observations. To put this in perspective, the observable universe is estimated to contain around 10 to the 80th atoms. The gigantic state space of the Atari games makes updating the traditional Q tables impractical. So how do we address this issue? We shift from directly computing Q values through value iteration to use a function approximation for estimating the Q function. Enter neural networks. These networks are designed to approximate the Q values for each potential action in a given state. Essentially, they work towards approximating the optimal Q function. This approach is the core of what we call deep Q learning. Deep Q learning is essentially the fusion of Q learning with deep neural networks. The deep neural network involved in this process is known as a deep Q network, or DQN for short. Now, let's explore how deep Q learning operates. Suppose we have a deep neural network tailored to accept states from an environment as input. For every state it receives, the network predicts Q values for every possible action originating from that state. The primary goal of this network is to approximate the optimal Q function, which aligns with the Bellman equation. The network's performance is evaluated by the loss, which is the difference between predicted and target Q values based on the Bellman equation. The loss helps us to quantify the network's accuracy in approximating the optimal Q function. Once the loss is calculated, we adjust the network's weights using methods like stochastic gradient descent and backpropagation. This cycle of loss calculation, weights adjustment, and refinement of Q value predictions is repeated until the network closely approximates the optimal Q function. After understanding the pre-processing and the input structure for the deep Q network, let's delve into the neural network architecture itself and how it processes these inputs to produce Q values for decision-making in the Atari game environment. In training an agent for Atari games, our approach involves processing a stack of 4 frames through the neural network representing a state. The reason we stack 4 consecutive frames together as a single input is to overcome temporal limitations. A single frame doesn't provide enough context to understand motion or direction. For instance, in the game Breakout, if we look at a single frame, can you tell which way the ball is moving? Not really. But when we look at a sequence of frames, we can discern the ball's trajectory. Stacking frames enable the network to capture this temporal information, crucial for understanding the dynamics of the game environment. From this, the network outputs a vector of Q values for each potential action in that state. However, before feeding these frames into the network, some pre-processing is necessary to streamline the training process. Firstly, we convert the frames to grayscale. This reduction is crucial as colors in Atari games typically don't provide critical information. And by converting them from 3 color channels to 1, we significantly reduce computational complexity. Additionally, we might crop irrelevant parts of the screen in certain games to focus on essential areas. This step further simplifies the input, making the training process more efficient. Next, let's consider the neural network's architecture. The input passes through 3 convolutional layers, which are adept at capturing spatial relationships within the images. Because these layers are stacked, they can also interpret the temporal dynamics across a sequence of frames. Finally, the network's output layer, a fully connected layer, plays a crucial role. It produces a Q value for each possible action in the given state. For a game where the actions are moving left, right, up, and down, this layer would have 4 nodes, each representing one of these actions. The value emitted by each node corresponds to the Q value associated with taking that action, given the state input to the network. This output is key for the AI's decision-making process, guiding it to actions that maximize expected rewards. In the training process of deep Q learning, we navigate through 2 main phases, sampling and training. During the sampling phase, the AI agent interacts with the environment, performing actions and observing the outcomes. Each of these experiments, consisting of the state, action, reward, and next state, is captured as a tuple and stored in a structure known as replay memory. This replay memory acts as a reservoir of experiences, enabling the agent to learn from a diverse set of scenarios, rather than being limited to recent or sequential experiences. Once we have accumulated sufficient experiences in the replay memory, we transition to the training phase. Here, we randomly select a small batch of these experience tuples from the replay memory. The agent then learns from this batch using a gradient descent update step. This involves adjusting the neural network's weight to minimize the difference between the predicted Q values and the target Q values, calculated based on the Bellman equation. So we've covered the essentials of deep Q learning and the structure of deep Q networks, as well as their functioning principles. But the question remains, how do you apply this knowledge to train an AI for your own video game? Fortunately, there's no need to start from scratch. Numerous existing libraries and frameworks simplify this process significantly. In the next video, I'll guide you through creating your own video game agent with just a few lines of code using Google Colab. Stay tuned. Make sure to like and subscribe. And until next time, happy learning.